Log on, tune in, find out. Another good idea from Cambridge.
This afternoon is Dave Woods. He will talk about block designs for non-normal data by conditional and marginal models.
Thanks, Alex, and thank you to the organisers for giving us this chance to talk here. I'm sure everything we talk about today will have, or in this talk, will have at least one too few random effects for Steve, but we'll carry on regardless. I'm actually changing the focus of my talk slightly, so I'm going to talk rather less about conditional models and rather more about marginal models, which in itself might be slightly contentious. So we'll start by looking at some introduction and some motivation and the type of experiments that we're thinking about here. And then we're going to look about designing some experiments where we're going to estimate our model parameters using from a marginal model and estimate the parameters using generalized estimating equations. And this is joint work with Peter van der Ven from the VU University in Amsterdam. Now I'm going to say a little bit about comparing conditional and marginal modeling paradigms from a design point of view and how we can design for both these types of models. And that will lead into some work we've been doing on designs for conditional models, for generalized linear mixed models, which actually Tim Waite will talk about after the tea break. So there's an increasing recognition that we need to try and think about experiments where we have a non-normal response. That obviously leads us to think about how we should try and plan and design these experiments. So some examples that I've been involved with in my own experience come from crystallography and aeronautics, and of course there's lots of examples in clinical trial type areas as well. So there's been a lot of work on designing experiments for non-normal responses, typically designing them for GLMs, particularly in the last 5 years or so. But they're always assuming that the experimental units are homogeneous. And often in these experiments, we haven't got that case. There aren't enough homogeneous units to run all our experiments under the same conditions, and we need to worry about blocks. So then the questions we have to answer are not just what treatment should we run, but how should we allocate the treatments to blocks, and then how should we actually analyze our data, what type of modeling should we use, and that clearly should help us define the experiment that we run. So we've got a couple of motivating examples. The first is from crystallography, and it's from the EPSRC National Crystallography Service at Southampton. And in this experiment, what they were doing was reacting an acid and a base together to form, well, hopefully to form a salt. So their experiment reacted the acid and base, and they saw their response was binary, did a salt form or not. There were various controllable variables in the experiment, including the stirring rate, the volume that they put into the wells they ran the experiment in, the temperature. In some of their equipment, they can actually vary the temperature on a per well basis, and the evaporation rate. And the experiments are run in these well plates in individual wells, and clearly there was at least a need to think about potential plate-to-plate variability. Our second example, which we'll spend a bit longer on, is from aeronautics. It's the cracking of the coating of engine bearings. So the coating of the engine bearing is sprayed onto a pair of bearings, and the factors the engineers were interested in investigating were the distance between the spray gun and the bearings, the angle that the spray gun swept through, and the speed at which it swept through that angle. And again, the outcome here was a binary outcome. The bearing passed or failed a visual inspection. Following on from something that Steve said, in this case, the engineers did try and do some kind of get a continuous measurement. They did a test on the bearings, which actually destroyed the bearings. So they didn't like it because it was destructive, and actually it didn't end up telling them very much about the cracking. So they did try, however, to come up with a continuous measure here. So in this example, our experimental unit is going to be a pair of bearings. That's the smallest unit to which we can apply a treatment. So we'll think about our response being the number of bearings that passes. So we can think about this as being binomial data with two trials. I'm going to ignore any potential correlation between those two trials or any potential over-dispersion, but it actually wouldn't affect the design under the modeling, under the method that we're going to use. What I am going to worry about is possible variability between the sessions in which the data is collected. So basically, this process could be done 4 times each morning and 4 times each afternoon. And in between these sessions, the operator could well change, the equipment might be reset. So we want to worry about possible session-to-session variability. But these sessions are just random mornings and afternoons. They don't really care too much about understanding that variability, but they don't want it to affect any inferences they make about the effect of these variables. So we're going to assume the sessions were a random sample for some bigger population, and that the observations within a block or a session are going to be more similar to each other than pairs of observations from different blocks. So if our observations were independent and if we hadn't heard Steve's talk, then we might just think we could use a generalized linear model to analyze the response from an experiment like this, and therefore we could design for a GLM. So we might use a probit regression because we might think there's a thresholding process going on here. So we might say our data is binomial and we have a link function that links the probability of success through to a linear predictor. And for the probit, that's the inverse CDF of a standard normal. And then, as I say, there's been lots of work on designing this, particularly recently there's been lots of work on multivariable designs which have been trying to overcome the problem that you always get, or usually get with nonlinear models, that the performance of your design depends on the values of the unknown parameters in your model. And so people have looked at taking a Bayesian approach or a pseudo-Bayesian approach, approximating these types of designs by clustering the support points of locally optimal designs, or doing sequential design for these problems. So this would be a method we could try and apply if we weren't worried about this block structure that we had. Alternatively, if we were worrying about the block structure but we were measuring and modeling a continuous response, then there's lots of literature we could use, try and take advantage of for thinking about random effect models for a normally distributed response. And these are just some of the design methods. It's not exhaustive, there's an awful lot out there, but some that are particularly relevant for what we're going to think about are looking at an algorithmic search to find the treatments and the allocation to blocks simultaneously, or allocating the blocks of some factorial or optimal linear model design, unblocked design, and allocating those treatments to blocks in some optimal way. Or you could get some theoretical results out if you're willing to make the restriction that the number of points, number of distinct points in your design is equal to the number of parameters. Okay. But we're kind of in neither of those situations because we have some non-normal data and we also want to worry about this potential correlation structure. So there are basically 2 modeling paradigms we can adopt if we're thinking about correlated non-normal data. So the first we've heard a lot about today is conditional or random effect models, where we have some random effects added to our linear predictor. In this case, Z would just be a matrix that tells us which treatment is in which block, and Tor would be just a vector of random block effects. So this is like a random intercept model. And the generalized linear mixed model is the most common form of conditional models, where Tor will follow a normal distribution, and if we're willing to make some different assumptions about Tor, we might end up with a hierarchical GLM instead. So most of the talk, I'm actually going to focus on the other modeling paradigm, which is the marginal model, which the big difference is we're not going to make a probability, we're not going to make many assumptions about the probability distribution, multivariate probability distribution of all of our data. So instead, we'll make assumptions about the first and second order moments. So the approaches here, you could use quasi-likelihood, particularly if you know the correct variance-covariance structure of your data. So for Poisson data, for example, we can make some progress on this front, and Neil Paris has a paper from a couple of years ago that does this. Or we could use generalized estimating equations, where we just make assumptions about the marginal first and second moments, and then we make a different assumption about the correlation structure. And that assumption is somewhat interesting, and we'll talk about that a little bit more. The marginal and the conditional models have been compared on various different cases. You see a lot of this work in the sort of social science type area, but there is a nice paper which compares them on industrial examples, more the type of thing that we're thinking about in this talk as well. So let's think a bit about the GE. So I'm going to abbreviate things to the GE model, where I mean a marginal model estimated, with the parameters estimated using generalized estimating equations. So we'll assume the marginal mean and variance for each observation, and that will generally be taken from an appropriate GLM. So it might be the probit case in probit model for our bearing experiment. And we assume this working correlation matrix, which tells us something about the dependent structure in our data, or at least it tells us something about what we're assuming about the dependent structure in our data. We need to be a bit careful with R, as we'll talk about later, because it typically will assume some structure for R, which for discrete data almost certainly cannot be the real correlation matrix. But I think as long as we're upfront about that assumption, we don't get into too much trouble. What we will assume is that R is going to be block diagonal. So observations from different blocks, pairs of observations from different blocks aren't going to be correlated, but within a block will allow some dependent structure. So as I said, we don't have a multivariate probability distribution for all our observations. Therefore, we don't have a likelihood function, which makes it our inference has to be based on estimating equations instead, and we therefore also don't have an information matrix for our usual design type issues, but we can still come up with an asymptotic variance covariance matrix. So when are we going to use models like this? It's perhaps almost easier to say when wouldn't you use a model like this. I think it's fairly standard to say you wouldn't use it if you were interested in subject-specific inference. And particularly if your blocks, for example, corresponded to subjects in a clinical trial, I don't think this would be a very appropriate model. But if we're interested in the marginal effects of the population average effects of the variables across the whole population of blocks, whole population of sessions, as we often are in these industrial type experiments, I think they are rather more interesting. So here are our estimating equations. They look a lot like the score equations for a GLM, except V would normally be our variance covariance matrix, and now we've put this working correlation matrix in here. So the problem you have with discrete data is that generally pairwise correlations depend upon the mean of the two observations. So we can go ahead and say, well, we're going to assume that R has, for example, some exchangeable correlation structure, but clearly our actual data when we get it, unless we run the same treatment in every, just run the same treatment for every observation, we're not going to get unlikely to get an exchangeable correlation structure. So we should think much more about R as perhaps being a weight matrix that adjusts the weight that's given to each observation to reflect the sort of average dependence that we think we have in our data. So we can also estimate, so we're going to assume that we have some parameters alpha which parameterize our correlation matrix. We can get other estimating equations out for those, or we can just fix it prior to the analysis. And there's a paper in JRSSB by Triganti and Joe, which looks at this, looks at the efficiencies of the estimators and finds they actually still are pretty good, and suggests some values for alpha to reflect different degrees of prior dependence. So alpha about 0.2 is, they suggest, for moderately dependent data. So under this estimating equation, we can get our asymptotic distribution out for beta hat. It's normally distributed, and our asymptotic variance covariance matrix is the inverse of this matrix M, which involves sigma, which is the true variance covariance matrix of Y, and typically that's going to be unknown to us. So clearly, if we're going to use this matrix for design purposes, we'll need to make some assumptions about this. You can kind of guess straight away what we're going to do. We'll just basically make the assumption that R is the true variance covariance correlation matrix for design purposes, and obviously when we get to the analysis we would worry about that again. But we will check a little bit about how robust our designs are to that assumption. So if we relate this back to our bearing experiment, so our marginal model here will be a probit regression model, so our mean and variance will come from the probit, and we'll assume an exchangeable working correlation structure so that pairs of observations in the same block will going to be equally correlated, and pairs from different blocks will be uncorrelated. So we get this block diagonal structure. Not sure if I said before, in this particular example, we could do 16 runs in 4 blocks of 4. So remember, there were 4, you could do 4 sprayings of a bearing per morning and per afternoon, and we'll do 4 of those blocks. So when we come to think about how we can select our designs, if we're going to use that matrix M, we do have to make an assumption. So the assumption we'll make is that the actual correlation is equal to the working correlation, so that we get sigma has this form, and we have a variance-covariance matrix, asymptotic variance-covariance matrix, or inverse of that, that looks fairly familiar to us. And is, as is usual with nonlinear models, this is going to depend on our unknown parameters beta, alpha as well. So to overcome this, we'll find a Bayesian or a pseudo-Bayesian optimal design. Pseudo because we're not actually going to suggest a Bayesian analysis to go along with this. So we will average, in this case, the log determinant of this matrix M with respect to a prior distribution on the beta parameters. What we won't do at the moment is assume a prior distribution for alpha, but we'll see later on that our designs actually tend to be quite robust to the value of alpha that we use in our working correlation. So the big problem we have left now is how do we approximate this integral. It won't typically be analytically tractable. So there are various ways we can do this. What we've done in this talk is just use a Latin hypercube sample in the parameter space and then average across those points, in this case 21 points. There are alternatives, which include doing a full Monte Carlo type approximation or using some form of quadrature. However we work out this objective function, we're going to assess our designs by comparing them to locally optimal designs. So what we'll do is we'll simulate a large number of parameter vectors from our prior distribution. We'll find the locally optimal design for each of those parameter vectors, and then we'll compare our robust design, our Bayesian design, to each of those locally optimal designs in terms of this efficiency, and then what we'll build up is a distribution of this efficiency induced by the distribution, the prior distribution on the betas. And we can use that distribution not just to say how robust a particular design is to the values of beta, we can use them to compare different designs as well. So there are multiple different ways we could define our block designs. We're going to mostly focus on exact designs, or we will think about picking exactly which n design points, which n treatments, which n design points we want to use and their allocation to blocks. There are multiple ways you can also think about defining a continuous design, one way of which would be to have fixed block sizes and then treat a block as a support point and find a weight for each block. So we'll come back at the end of the talk, we'll talk a little bit about continuous designs, where if we have a continuous design, we can develop a general equivalence theorem to check the optimality of the designs, but mostly we're going to focus on exact designs here. And we're going to look at two different ways of finding these exact designs. The first is to simultaneously find the treatments we want to run and their allocation to blocks using an algorithmic search. And the second is to take the optimal GLM design and find an optimal allocation of that to blocks with respect to our working correlation matrix. So we'll compare these two methods on our bearing example. So we'll have a probit regression model. Our linear predictor will have linear terms in our three factors and the interactions. We'll get 16 runs in 4 blocks of size 4, and the results, the actual designs I'll show you, will be for alpha equals 0.2 in the working correlation. Our prior distribution for beta can be made up by independent uniform distributions on each of the betas. Each of these have the same length, the same amount of prior information that is shifted away from 0. So to do our simultaneous optimization, our algorithmic search, we've used simulated annealing. There are lots of other optimization algorithms you could apply. This particular algorithm does a continuous optimization for each point. So what we get is we do a random perturbation of each design point, and we accept or reject that point based on how much it improves or doesn't improve our design. We're always going to accept it if it improves our design. If it doesn't improve it, we still might accept that change to the design with a probability which is inversely proportional to the decrease in design performance. And these sort of stochastic kicks help us avoid local optima or get out of local optima. And what we do is we reduce, or we reduce this acceptance probability for bad moves and the perturbation size as we sort of cool the algorithm and move through the iterations. So we end up with a greedy algorithm just making small moves in our design space, hopefully towards an optimum. So here is our design that we found for alpha equals 0.2. So each of the panels is a block of size 4. This is obviously the value of our factor x1, x2, and the colours, if you can see those, give you the values of x3. So all 4 blocks are different, and in fact there are 16 distinct points in this design. Each of the different factors has a number of levels. It's certainly not a 2-level design. But most of the points are on the boundary of the design space, which is -1, +1. There's only one point which is actually on in the interior of the design space. And that's probably something to do with the ranges we assume for our priors for beta. So our second approach is to take an optimal design for the GLM and then allocate those treatments to blocks in an optimal way. This is going to be particularly useful if you're finding locally optimal designs, because there's an increasing amount of literature on analytic locally optimal designs, which are going to help you make this a much less computationally intensive problem. Once you've got your optimal design, you can just use an interchange algorithm, for example, taking account of our working correlation structure to assign the treatments to blocks. So we're not finding locally optimal designs. So our optimal GLM design, our Bayesian design there, we found computationally as well. Then we allocated it to blocks. The design looks very similar to the previous design that we saw. It's not exactly the same. In particular, if you notice the values of x3, these are different from the values of x3 we had in the previous design. But again, we have multiple levels for each factor. We have 16 distinct points. And again, actually only 1 point on the interior. So they look very similar. The question is, do they perform very similarly? Well, we can do this simulation-based performance assessment to try and see what's happening here. So again, this is where we've generated, in this case, 10,000 parameter vectors from our prior. From each of these, we've found the locally de-optimal design, and we have then worked out the efficiency of our 2 robust designs. If you just think about this plot to start with, we've got 2 robust designs, and we found the efficiency of each of these with respect to each of these locally optimal designs. And what we then get is a distribution of efficiencies, which is summarized in these box plots. So we've done this not just for the 2 designs that I showed you, but also for designs found with alpha is 0.4, 0.6, and 0.8. And what we can see is the designs actually perform very similarly to each other. For larger values of alpha, there's a slight improvement in performance if we simultaneously choose the treatments and the blocks together, the algorithmic design. For smaller alpha, that's perhaps reversed slightly, and we get a slight increase in performance from the design that allocates the treatments to blocks. The other thing is the designs are pretty robust. So particularly the lower quartiles of these things are always at least, I think, about 0.64. So we don't generally lose that much performance across the design space, the parameter space rather. We can also directly compare the 2 designs. So if we do this, these are now empirical distributions of the relative efficiency of the algorithm design compared to the allocated design. The only real reason to show you this plot is that although the performances are quite similar of the 2 designs, what we can get here in this plot, we've got quite a long right-hand tail here. So occasionally the design which simultaneously finds the treatments and the allocation can be a lot more efficient, up to 20–25% more efficient than the design that allocates the treatments to blocks. And that design is never more than 10% more efficient than the algorithm design. So I think I've said all of those points. What we haven't worried about yet is the robustness of the designs to this working correlation parameter alpha. So what we've done here is we've taken the designs that we found using alpha equals 0.2, and we've done this simulation-based assessment on them, but for different values of alpha. Alpha equals 0.4, 0.6, 0.8, and also 0. And what we see is these are the median efficiencies from the simulations, and we can see they actually hold up extremely well. They actually improve as you increase alpha. And that, I think, is symptomatic of the fact that the designs appear to be more robust to beta for larger values of alpha. The other interesting thing in this table is when alpha equals 0, then there is no blocking structure. There is no working correlation structure in our data. And of course, the allocated design here is the optimal design in that case, right? It's a Bayesian optimal design for the GLM. So what we can see is we actually don't lose any performance really by accounting for the correlation structure or the working correlation structure when we find our design. So of course that does make you wonder did we need to worry about the working correlation structure at all if they seem very robust to alpha? Well, what we've done here is try to answer that question by taking, I think again it's 10,000 different random allocations of the optimal GLM design to blocks. And what we can see is if, particularly for larger values of alpha, where obviously there's quite a strong dependence structure in the data, if we pick allocation at random, we could get unlucky and actually end up losing a lot of efficiency, up to 50% efficiency for large values of alpha, but still up to 30% efficiency for small values of alpha. So you do need to think a little bit about this when you're planning your experiment. Now, we have made this assumption when we're finding our designs that our true correlation is equal to the working correlation. And I did say that in general that's not actually going to be possible because for discrete data, the pairwise correlations depend upon, in the binary case, they just depend upon the success probabilities. So we've tried to investigate a little bit how robust our designs are to this. So what we can get is a bound on the pairwise correlation between two binary observations. And what we've done is we're going to create a new, essentially a different working correlation matrix based on this bound. So we'll set the pairwise correlation between two observations to be equal to the minimum of this bound and a parameter alpha, which we'll specify. And this is going to allow us to say what happens if our actual correlation structure is smaller than there's less correlation than we're assuming in the working correlation, or if there's stronger correlation than we're assuming in the working correlation. And clearly, of course, also this, we'll call this matrix we construct like this R star, this isn't going to be structured. It's not going to have the same structure as we're assuming, for example, with an exchangeable correlation structure. So we can have a look and see how our design performance holds up under this. And the way we'll investigate this is empirically by taking a set of designs and comparing their performance under the objective function that we've been using to find our designs, where we assume our true covariance structure comes from our working correlation, and then this objective function, which is basically the same, but rather than plugging in the working correlation in here, we'll plug in this correlation derived from the bounds, and we'll try and get an idea of what happens if our correlation is smaller or larger than we're assuming. So what we've done, have to remember how many designs are in these plots. I think what we've done is generate 1,000 what I'll call efficient designs. So what we did, so this is all done for the bearing example again, so 3 factors and that linear predictor that I showed you. So we generated 1,000 designs by running our simulation annealing algorithm with kind of rough parameter settings. So we didn't get the best design each time. We've got a selection of designs which are all pretty efficient. These are the black dots. What we then did was find 500 designs whose points are either -1 or +1 at random, and these are the green dots. And then we found 500 designs whose points are picked at random from the interval -1, +1, and these are the red dots. And what we've done here is plotted the value of the objective function, assuming the working correlation is the true correlation, against the objective function derived from these bounds. And in these plots, we've set this parameter gamma here equal to alpha in each case. And that means that the correlation from the bounds can only be smaller than the working correlation that we're assuming. And what we can see that certainly for small working correlation, then we're getting almost perfect agreement. As alpha gets bigger, we get more spread on these, and that makes sense because actually a pairwise correlation of 0.8 is highly unlikely to occur with these types of binary data. But what we can see is that in each case, the black dots, the designs we found under our essentially optimal designs, they perform well under both measures. So in each case, they are optimal or near optimal, even under they are the best amongst these designs under our bounds as well. And we can do the same thing, but assuming this gamma parameter now is 0.9, and this means that our actual correlation can be higher than our working correlation now. And we can see we get a bit more spread in these plots, particularly the smaller values of alpha, but that ranking is still essentially maintained. If you're interested in why under our objective function we get this split in these green designs, if I remember rightly, this set all have at least one block that has a constant treatment applied to it, and these ones do not, which is an interesting little side issue. Okay, so I've got at least 5 minutes left. So I'd like to finish just by almost giving a trailer for some of the stuff that Tim's going to talk about after the tea break. So we've looked at finding designs for these GE models, these marginal models, and we could of course also find designs for the corresponding random effect models. So if we just consider an example of this, let's consider a Poisson example this time. So under the marginal model, our mean and our variance is going to be equal to mu. Under the random effect model, we'll have that conditional on our random effects. We have a Poisson distribution. We'll have the log link, and we'll have a quadratic linear predictor where we'll just find locally optimal designs here. So we'll have a linear effect of 5, quadratic effect of 1, and of course our conditional model will have a random intercept in there. So we're going to find some designs with blocks of size 2, so very small blocks, admittedly. Under the GE approach we've been looking at, where we'll have a working correlation of this form. We have no real choice about our working correlation here, of course, because our blocks are only of size 2. We'll also find designs under a quasi-likelihood approach, where we'll make the same assumptions about the marginal mean and variance, but because we've got Poisson data here, we can actually derive the closed form for the actual variance covariance matrix of Y, and we can plug that into the estimating equations. And this is essentially, for a different example, so what Nia Paris did. And we'll find designs under the generalized linear mix model where obviously we'll have to do some approximations to get rid of some of these tricky integrals to get the marginal likelihood. And the approach we're taking is loosely based on the marginal quasi-likelihood approach, which was popular in the modeling analysis literature 15 years ago or so. It's kind of been overtaken there, but it's still, I think, quite useful for design purposes because it's nice and analytic compared to some of the computational approaches we can make. So this is what Tim will talk a lot more about after tea. But what we'll just do a quick comparison here. So we're finding continuous designs now rather than exact designs, just to try and confuse us. So our continuous designs come up with a set of support points, which of course in this case are blocks of size 2, and the weights that correspond to each of these. So this is our GE design, for example, which has 3 support points, so 3 blocks, which you were sort of template blocks, and the weights you would give to each of them are, in this example, the design we get out by making the quasi-likelihood assumptions or the GLMM assumptions are actually the same, and that just has 2 blocks which are equally weighted. So for these locally optimal designs, we took alpha, our working pairwise correlation, to be equal to 1/2, and we took sigma squared in our random effects distribution to be equal to 1/2. The reason we chose the latter of those two was if we actually look at the intra-block correlation between these two designs, in this design, the average inter-block correlation across the 2 blocks is nearly equal to 1/2. So in some sense, we're trying to make these comparable. So because we've got continuous designs, we can check the optimality of these designs using the general equivalence theorem. So these are plots of the derivative function. If you can see them, the red diamonds give us the locations of our support points. So this will be point 1 in the block, this will be point 2 in our block. and our GE design has 3 points, and our quasi and GLMM design have 2 support points. Support points are at optima of the derivative surface. Derivative surface doesn't go greater than 0 anywhere, so there's some reasonable evidence that our designs are optimal. They're quite hard to check because we've got essentially a continuous space, but it's in more than one dimension. We can also look at the efficiencies of the designs under the alternative modeling / design methods. So if we find our design assuming this GE approach, we can see that it's around 87% efficient under the quasi likelihood and GLMM approaches, and the other design is around 0.9% efficient under the GE approach. Now obviously these designs and these efficiencies will change a bit as we alter alpha and sigma squared to find different designs and perhaps get different efficiencies, though in this case, probably because of the small blocks, the designs are very robust to alpha and sigma squared, and these efficiencies only change by a percentage point or 2. Right, so we've kind of looked at developing a suite of methods for designing and analysing these blocked experiments. On the analysis side, we've also looked for the GEs at trying to address the problem of separation, which can occur when you run small experiments. And we've seen it's important to take account of blocks when designing our experiment. We can look at other working correlation structures if we want to, such as autoaggressive, nearest neighbour, and the designs are quite robust to those assumed structures. And we can generalize this methodology to also take account of uncertainty in the linear predictors and the link functions. So the work that we're doing now that's ongoing is looking at optimal designs for the conditional models. So we're looking at optimal designs for GLMMs, and this is joint with Tim Waterhouse from Eli Lilly and Tim Waite, who's going to talk about it after tea, or some of the work after tea. We're also thinking about optimal designs for the hierarchical GLMs as well. And that's work that we're doing with Peter van der Ven. So what we might be able to do eventually is essentially expand that example I had at the end of my talk to try and look more generally for connections between the different methods and the designs that we get. Thank you.
Okay, any questions for Dave? Comments as well? Yes, please.
I want to draw your attention to a couple of alternative approaches, especially when you use probit regression with normally distributed random effects. So the first is beta binomial model.
Yeah.
In beta binomial model, you get a closed form expression for the mean, and you get this over dispersion parameter as a part of your random effects. Another way to make your statistical inference is to take the expected value of the probit under a random effect. And there is a nice closed form solution for expected value of the probit with the random part. So it basically, you attenuate your coefficients.
Right.
So you can do this as well.
Thank you.
Interested in your general equivalence theorem applied to the generalized estimating equation. When you presented that, there was a set of equations. So what exactly is the criterion?
Well, we've got this matrix M, this asymptotic variance covariance matrix, which is almost the same as you have for GLM. So it's essentially the same operation. We can look at the log determinant of that and take the derivatives.
Any other questions, comments? I'll try to ask you one question. The size of the blocks, at what stage do you choose them and how do you choose them?
So that's interesting. We're very much coming from the kind of experiments that motivated this work. The block sizes were fixed by the experiment. They're a feature of what's happening. So we're very much coming from the point of view, even when we look at the continuous designs, we're fixing that block size because of some feature of the process and then finding designs for that. There are other ways you can define continuous block designs, for example, where you actually essentially have the block design, the blocks themselves able to be different sizes, essentially. And in that case, what you often end up getting is that the blocks essentially expand so that you can have as many support points inside the block as you need to estimate your model, and you end up running the same block multiple times. So that's the type of experiments I think that Rainer was talking about this morning.
I suppose it's just possible that you might be able to do sort of 5 and 3 or something like that.
Different sizes.
Yes,
blocks.
I mean,
Yes.
not. You know, so you can set up a whole series of designs, dividing into 4 blocks of all sorts
Yeah.
of sizes. It might be that they don't get up very early in the morning, but wait. You know,
Indeed, in that case, yes.
It's
yes.
just possible
Yes.
there could be a big change in efficiency, but
Right.
extremely unlikely, of course. Yeah.
Other questions, comments? Yes, no, so thank you very much again.
Thank you.